Hello and welcome to this tutorial session on the week 11. So in this tutorial session, what we're going to do here is we will be taking upon the questions and of the power system engineer. And this before I start this session, I would like to introduce myself. I Mohammad Owais Khan, Prime Minister Research Fellow, Electrical Engineering Department, Aligarh Muslim University. I hope I am audible to all of you. So let's start this session. So you have been gone through the lectures at NPTEL where where there has been a discussion going on upon the load frequency control and of two area and how we can do the stability analysis, okay, and how to control the automatic how to control the frequency. Before I start, we have been gone through the multiple times why the frequency control is important. I have gone through in the last lecture is that because the fluctuation in frequency will cause various issues, like it will cause the generation losses, and it will lead to the variation in the supply, which may inadvertently will cause the damage to the appliances. So we have been talked through for the last 2 weeks. So, and I have also talked about I have also talked about various mm, various models of generators. Okay, generator models. We have been talked about that also, and in this, I will just a second. So basically, we also talked about various generator models in the last time, and we also talked about the two area load frequency control. Like for example, let me again revise here. Let's say there is a control area 1 and there is another control area 2, and we have a tie line which is connected to this. So that tie line, the power which will transfer on this tie line will be equal to, let's say, P tie, P tie, which is equal to V1 V2 X12 sine del 1 minus del 2. Okay. Now, if there is any incremental change in del 1 and del 2, the incremental power will be like del p tie, which is incremental power. It will be difference between the change in angle 1 to angle 2 multiplied by T12, which is a whose value is this much. Okay. So here, this is the incremental power when there is a change in the frequency. Based on that, we can calculate what we can calculate. We can calculate the power in the tie line, which is equal to 2 pi T12 integral of del F1 dt minus del F2 dt. Okay, these are the frequency which relates to the angles. So, and based on that, if we integrate that all like we have also derived an equation which is known as del Pg minus del Pd equal to 2h by f d by dt del T plus b per unit multiplied by del f. This equation relates the change in angle with the change in power. If somehow we been asked like how we are going to calculate no delta t or all this, we can calculate here. We also convert this equation into a lap by using the Laplace transform. How we can even convert that? Based on that, and if we convert this equation by using the Laplace transformation, the last class we have done that quite clearly. So what happens here is that the function, a block diagram we achieved, which is like I will draw it here. You can go towards those like notes which I have given already with to shared with you. Okay, this is the block diagram we developed last time, and it is del Pg1 del Pg1. Here it is given plus this thing we also developed last time here. What is del P tie, and this is the del PD. This is the block diagram we discussed, and based on that we calculate the del Fs. Okay, if we know these things, we can calculate the change in the frequency. Okay, so basically what we will do here, because we have already gone through the concept, we will start solving some of the questions. Okay, and based on that questions we will solve, we will understand how these things works. Okay, because already you have gone through the theoretical aspect on the lectures, and I have also gone through in the last week. So let me give it to you one more thing. We will solve more questions today. Okay, the questions we will be solving only questions today. Okay, so because concept I have already given to you. So basically, let me get questions for you. Okay, because theoretical you can go there on the lectures, or I which PDF which I have provided. You can go to those lectures and understand that. Okay, so let's move on towards questions. Okay, just a second. Okay, wait a second. Just a second. Okay. Hmm. We will solve different types of questions. There will be MCQs today. I will be giving you some MCQs also, so it will, you know, better understanding will be done for you. Okay. A load is supplied by a 440 volt 50 hertz source. The active power P and reactive power Q consumed by load are such that P varies to 12 to 50 and Q varies from 7 to 10. Okay, find the minimum power factor that can be observed across load when an overexcited synchronous condenser at no load is connected across the load generates 6.0 kVAR reactive power. Options are 0.9487 lakh. Okay, options. Let's just get into that. Okay, so we will solve it. The question is given: a load is supplied by a 440 volt source. The active power, and the reactive power Q consumed by the load are such that this is the range of the power consumed. We have to find the minimum reactive power, minimum power factor. Okay, so let me solve it for you. For a minimum power factor, first the reactive power consumed by overexcited synchronous condenser is, let's say, QC is equal to 6 kVAR. Okay, and P load is P minimum is equal to 12 kilowatt. Then Q load is Q maximum equal to 10 kVAR. Okay. So for a minute, अभी हमने why we are taking the minimum and maximum of the load, because for a minimum power factor, P source divided by under roots P source plus Q source. Okay, for a minimum power factor, this should be minimum, and this is in the numerator, this should be maximum. So P source is here, it will be 12. Q source will be, now first let square plus, now Q source. Source will supply only those reactive power which is the difference between the load and the QC, because from 6 kVAR will be provided by the QC and remaining will be provided by the load. So for a minimum, this should be Q load minus QC. So it will be how much? 10 minus 6 whole square. So it will be 12 upon under root 144 plus 16. It is 12 upon under root 160. Okay, I think it will come out to be 0.9487 lagging. Okay, because it is in an overexcited phase. Okay, so now next question. I hope you understood this. We will now today we will do questions. Okay, so consider the following statement regarding load frequency control. Okay, so first is time constant of automatic load frequency control is about 15 seconds. B. Integral control eliminates static frequency drop. In the tie line, bias control, the control signal for each area is proportional to change in frequency as well as change in tie line power. So basically, we have to found give the correct answer. So just a second, let me see. There are various options for it because multiple options are correct. A 1, 2, 3. B 1 and 3. C just a second. C 1 and 2, 1 and 3, and D 2 and 3. So basically, this is the solution. Okay, now what happens here is that what is given in the question is consider the following statement regarding the load frequency control. First is time constant of automatic load frequency control is about 15 seconds. Second, it says that integral control eliminates the static frequency drop. Okay, so basically what we have to here see, consider the following. Just a second, let me see. One more. Yes, we have to find which of the following are correct. Okay, we have the following. Check the correct. Okay, okay. So in the third says, so what happened here is that in case of an automatic frequency control, the uh, integral control eliminates the static frequency drop, and also in the tie line load it also controls the signal. Okay, it also controls the signal for each area, and that signal is proportional to the change in frequency and the change in the tie line. Okay, we have already gone through this in a that. So and first option says time constant is about 15 seconds. No, no, it's not correct. So B and C. What I have done here, I have changed the options. Oh, just a second. Let okay, okay. So these are one, these are two, these are three. So basically, two and three is the correct answer. Okay. Now next question. A negative area control error means that the area is not generating enough power to send the desired amount out of that area. B, area is generating more power to send the desired amount. Area is not generating enough power to send the desired amount of out of the area. Area is generating more power to set the desired amount out of the area. The area is generating power to meet its own requirement. Okay, its own requirements. Okay, so we have to calculate the we have to give the which of the following is the correct. Okay, so here in this question it says that a negative area control means. So first of all, I would like to introduce what is an area control means. Area control error, sorry, area negative area control error. Area control area control error is equal, let's say this is ACE, it is equal to the tie line power minus the scheduled power plus B into change and the frequency by constant multiplied by the change in the frequency. So, which means a negative area means that area is not generating enough power. That's why the area became negative. And why? So what happened here is that it cannot send the desired amount out of the out of that area for like for any area. There is a generation going on. There is an scheduled power. There is a tie power line. If if the area control error is negative, it means it cannot send the power out of the desired amount out of the area. So basically, A is the correct option. Question: a frequency sensitive load connected to a 50 Hz power system changes by 1.15% for 1.10% change in frequency on 10 MVA system base. If the system base is changed zero point 0.5 MVA, the value of D in per unit megawatt, actually D is per unit megawatt per hertz, where what we call D is, we have already told you about in the last lecture. D is the frequency sensitivity constant. Frequency sensitivity constant of load. So what value it possesses? What will be its value? Anyone who can do it? We have solved various questions on this also. What is D? It is the frequency sensitive constant. So it will change. D is the percentage change in load divided by the percentage change in frequency. Percentage change in frequency. How much percentage change in load is 1.15 into 10, because 10 MVA is the on a on a system base, ठीक है? And percentage change in the frequency 1.1 and frequency is 50. So it will cancel it out and it comes out to be how much? It will come out to be 0.42 per unit megawatt per, just a second. One thing more. One thing more. Just a second. Now what happens here is that it is in D is always in per unit. We have it is in per unit. So here in the question it given if the system base is changed to 0.5 तो हम क्या करेंगे 10 को डिवाइड कर देंगे 0.5 से तो इसका सिस्टम बेस चेंज हो जाएगा तो इसका आएगा 1.15 into 10 divided by 0.5 divided by 1.1 into 50 so it will come out to be 0.42 per unit megawatt per hertz okay so this the value of I would say the value of D comes out to be 0.42 per unit megawatt hertz. Okay, so now moving on towards the next question. Now let me give you a question and you have to give the correct answer in the chat box. Okay, I am waiting for the answer. I will wait for the answer. Okay, just a second. Let me see. Which term models the frequency sensitivity of load? Okay, H, T, G, C, both H and TG, and D is capital T. So give in the chat box the correct answer to this. I'm waiting your answers. No one? Everyone fall asleep? See, let me see. No, अभी बता. Just told you. What is the D? What is D? It is a frequency. क्या था D? Change in load divided by change in frequency. So D answer. Okay. Okay. Another question. What is the effect of increasing the droop constant R on the system frequency stability? A. Improves the frequency response. Makes the system stable, unstable. C. Reduces the frequency deviation. D. Increases the steady state error. So, इफेक्ट क्या होता है? Higher the R, higher the value of R, higher the value of R, it reduces the participation of the generators, okay, generator, which will lead to a increase in the steady state error. So D is the correct option. Okay, let's solve another question. Okay. A 50 hertz small system consists of five identical 300 kVA generating units feeding a total load of 0.9 megawatt. The inertia constant H of each unit is 6 on 300 kVA base. The total load varies by 5% for 1% change in frequency. Speed regulation characteristics is 1 Hz per unit megawatt. When there is a sudden increase in a load of 100 kilowatt, find the steady state frequency. We have to assume the governor loop is inactive. Okay, so we will solve some questions we will solve this question. So options are given. Just a second. Four. Okay. So let's solve this question. So what is given here in this? The system MV, system base MV. It is 5 into 300 upon 1000 equal to 1.5 MV. Okay. System load PL. It is equal to zero point 0.9 plus zero point 0.1, which is equal to 1 megawatt. Then comes the load damping parameter. D equal to 5 into 1.0 divided by 1 into 50. This is the load damping parameter. Okay. So how we calculate, which is also known as the frequency sensitivity. So let me D, how we calculated D. We just we know the steps. There is a 5% change in the load. Okay, 5% change in the load, and how much is the total load? We have of total load of zero point 0.9, but system load we add zero point 0.9 plus zero point 0.1. Okay, it will come out to be, because there is a increase of 100 kilowatt, so it comes total load will come out to be 1. So 5% of 1 into 5 into 1 divided by 1.1, sorry, 1% of frequency, which is 1 into 50. 100 will cancel out of them, so it come out to be how much? 0.1 megawatt per hertz. Okay, now what happens when the governor is inactive? The speed deviation del Fs comes out to be del PL divided by D minus. What is change in load? Del PL is zero point 0.1, because the load sudden increase is of zero point 0.1 divided by zero point 0.1. It will come out to be minus hertz. So speed deviation, the frequency deviation due to this is will be minus 1 hertz. So steady state frequency is 50 minus 1, which is 49 hertz. So this is the final answer of this question, which is the we have to calculate the steady state frequency. So let's move on toward another question. Hmm, So let me give you one more question, which is a very better. Okay, now another question. In a PID based LFC system, doubling the integral gain K affects the steady state error by A. Reducing it to half, B. Eliminating it, C. Doubling it, D. No effect. So basically, what does an integral action does is eliminate the steady state error. So it is the right option is B. Okay. Now let me give you one more question. In a in a multi-area system, negative ACE indicates that the area is importing power, B. Exporting power, C. Excess generation, D. Has insufficient generation. So, as I have said here, the negative area means the amount send it cannot send it can just a second. It cannot send it cannot send the desired power out of the area. Why? Because it is not meeting the export and import load and the export commitment. So therefore, it has a insufficient generation. So now another question here. For a system For a system with D equal to 0, the steady state frequency deviation after a load change depends on first option inertia constant, B speed regulation, C tie line stiffness, D governor time constant. Okay, let me see. Yes. So for a system with D0, the steady state frequency deviation of a load, it depends only upon the speed regulation. Okay. How del F is equal to minus R del P. Okay. So now let's move on to the another question. The primary objective of tie line bias control is to first maintain frequency at nominal value, B maintained scheduled tie line power, C both A and B, D minimize generator wear and tear. Okay, so it's very quite clear. The objective of the tie line bias control first is to maintain the frequency, and it also schedule the power, tie line power. Okay, another question. Let's solve that. So, question is given for isolated generating station with local load is shown in figure. Okay, it is observed it is observed that del PL is equal to minus 125 per unit, brings the del W is 0.20 per unit. In the steady state, find the value of R. Find the value of R. Take del PC 0. So here it is given. Uh, just a second, let me give. This is a block diagram 1 by R plus del PC. The control function is 1 by S plus 1. Editing. Another function is del. Another signal is coming del PL. Function here is 1 plus. Block function is 1S. It goes toward the W. Like this, it is connected. This is del W. So basically, we have to find this. So first of all, we should assume this is equal to 0. So how we solve it? Solution. So first of all, it is 0. This is the input. Like if that del PC is 0, okay. So here del W comes out to be 10 upon 1 plus 10s. You should use your control system block reduction techniques. It will easily come out to 1 upon 1 plus s del W minus del PL. Okay, so if we take it toward here, so it will come del W come out to be how much? Minus del PL divided by, actually this is multiplied by both. So here 10 1 plus 10s is same, and it will be 1 minus 10 upon 1 plus 10s, okay, 1 by R minus 1 plus S. You should use any block reduction technique, you can come to this, or you can use the signal flow graph technique, okay. You can get you treat this as an input and treat this as an output, so you can easily calculate this. So the output input relation come out to be how much? This is minus 10 by 1 plus 10s divided by 1 minus 10 upon 1 plus 10s minus 1 by R multiply by 1 by 1 plus S. So now we have to find the steady state. So for steady state, ESS, just a second. For steady state, limit del W S tends to 0. So if we put S tends to 0 here, what it will be? This goes out, this goes out, this goes out. So minus 10, 1 minus 10 multiplied by minus 1 by R. So it comes out to be minus 10 divided by 1 plus 10 by R and multiplied by del P. L also. Okay, this is del PL. So limit s tends to 0, del W comes out to be 10 minus 1 plus 10 by R. Okay, and del PL is here. In the question it is given, take del W 0.20 and del PL minus 0.125. You can see here. Okay, so put this in this equation, 0.20 minus 10, 1 plus 10 by R multiplied by 0.125R, and we will remove this minus sign. So it will be 0.20 point 1.25 1 by 10 0.20 plus 0.2 multiplied by R equal to 1.25. I think I have done correctly. Yes. So it will come out to be 2 by R is equal to 1.25 minus 0.20. So it will, how much it will be? So 5, 0, 1.5. So R comes out to be 200 divided by 105. So it will be around 1.95 per unit, zero 0.5 per unit. So the value of R is 1.905 per unit. Okay, so I hope you have understood this question quite clearly. Now, moving on towards another question. Now, in this question, there is second part also. Now, we have to find the value, find the value of, find the value of del PC so that it brings del W to 0. Okay, so here the block diagram gets modified. Now here the block diagram is like this, 1 by R del PC plus, now we cannot put del PC 0. So using signal flow graph or block reduction technique, it's very easy. Del PL del W goes outside like this. So base using signal flow graph. I'm not going in details how we are going it, otherwise I'm not be able to solve this question. Okay, because we have to solve different questions also, and this is a power system. So you can, I hope you know the how to implement that signal flow graph. Del W 10 1 plus 10s multiplied by 1 minus, sorry, minus 1 by R del W plus del PC 1 by 1 plus S minus del PL. Okay. Now again taking W parts on the left side and rearranging. So del W comes out to be 10 by 1 plus 10S divided by 1 minus 10 by 1 plus 10S minus 1 by R into 1 plus 1 by S, and this is multiplied by 1 by 1 plus S del PC minus del PL. Now in this question we have to find the value of del PC when S is W is 0. So similarly we will use S tends to 0, del W is equal to 0. If we put that, now what happens here is S becomes 0. So this gone, this term gone, this term gone, this term gone. So remaining is minus 10 divided by 1 plus 10 by R del PC minus del PL, and its value is 0. So del PC is equal to del PL. It come out to be minus 0.125 per unit. So for to become del W 0, to make del W 0, we the the required value of del PC is minus 0.125, or we can say here which is equal to del PL in a more general term. So I hope this question have pretty much understand uh, the concept. Okay, let's solve this question. In this question it is given, consider a two area system connected with lossless tie line with speed regulation R1.03 per unit and R2.05 per unit, and the damping factor is D1 is equal to 0.8 per unit and D2 is equal to 0.5 per unit. Base volt ampere of each area is 100 MVA. Area 1 is subjected to a load decrement of 10 megawatt, and area 2 is subjected to a load increment of 15 megawatt, find out the steady state frequency deviation. The normal frequency is 50 Hz. No control action is activated. So here what is given, that there are two areas of the power system which is connected by a lossless tie line, and each area has the speed regulation factors like this and the damping factor D1 and D2. The base VA of each area is 100 MVA, and what happens to the area 1 is that it is subjected to a load decrease of 10 megawatt, and consequently area 2 has been subjected to a loading increment of 15 megawatt. So what we have to find out, we have to find out the frequency deviation at the steady state, and the nominal frequency in this is 50 Hertz. Okay, so the solution of this question is, so first of all, in area 1 the change in the load is minus 10, it is decreasing. Okay, so and the base MVA here is how much? It is 100. So in per unit, del PL1 PU is equal to minus 10 divided by 100 minus 0.1 per unit. Okay, similarly del PL2 in the second area there is an increment of the load, so it will be plus 15 megawatt. In per unit it is del PL2 which is equal to plus 15 divided by 100, it comes to be 0.15 per unit. Now to calculate the steady state, to calculate frequency deviation at steady state, we have to find the effective beta. Like we will use this formula which is del F. We know that del PL1 plus del PL2. Okay, and it is on the similar lines we will use, as it is for a two area system, we will calculate the effective beta. So what is beta? Here beta is D1 plus D2 plus 1 upon R1 plus 1 upon R2. Okay, so now based on the information given, first we calculate beta. What is D1 here? We know that D1 is 0.8, D2 is 0.5, R1 is 0.03 and R2 is 0.05. 0.8 plus 0.8 plus 1 upon R1 which is 0.03 plus 0.05. So if we calculate it, it will come out to be like, let me calculate it first. So zero point 0.8 plus 0.8 plus this value comes out to be 33.33 plus, and it will be 20. 1 divided by 0.05 is 20. So if we add it, it will come out to be 54.633 per unit. Okay, so the effective value of beta for two areas comes out to be this. Now, putting this thing in the equation, del F del PL1 del PL2 beta minus. So what is del PL1? It is minus 0.10 plus 0.15 divided by 54.63. So del F is equal to 0.25 divided by 54.63. So if you multiply it, if we solve it for this, it will, sorry, just a second, it will come out to be 0.05. Okay, so now if we divide it, its value I think comes out to be 0.00095152 per unit. So if you multiply it with the base value, because it's in per unit, we have to calculate in the hertz. So frequency deviation at steady state is del F multiplied by F normal. So what is del F? 0.00095152 into 50, and it comes out to be, it is in minus. Okay, so minus 0.04576 hertz. So the deviation is frequency deviation, if we write it at steady state, is minus 0.04576 hertz. This is the answer. So this is how we are going to solve this question. Now coming towards the next question. So in the next question, a system with H 8 seconds loses 200 megawatt generation. Calculate the initial ROCF, rate of change of frequency, in hertz per second if the base MVA is 1000. So the options are A 125 hertz per second minus 0.250 hertz per second minus 0.500 hertz per second, d minus 1.00 hertz per second. So we have to calculate the initial rate of change. We know the initial rate of change of frequency del f by del t is comes out to be del p upon 2h. It is from the formula which we have derived early on in our lecture, in the last lecture. So basically from here we are going to take this. So what is del p? So it is, so what happens here is that, what is del p? So del p is in per unit is 200 divided by 1000. So it comes out to be 0.2. So minus 0.2 divided by 2 into h, which is 8 second, into multiplied by the frequency, which is here it is 60 hertz. I think I have given in the question. No. So the nominal frequency is 60 hertz here. Okay. So if we calculate it, it comes out to be around, let me calculate this value for you. 60 divided by 8. So it will come out to be 7.5. Okay. So let me see what are the options. Okay, one option is wrong here, which is minus, it is will be minus 0.75. Okay, so it will minus 0.75 hertz per second. So based on this, the correct option is B. Okay, now moving on towards another question. The inertia constant, the inertia constant h affects first voltage variation, B initial frequency variation, no sorry, response, C steady state error, D governor speed. So what does it affect? Actually, the inertia constant has an effect on the frequency response. As you can see here in the equation which we derived early on based on the transfer function, the frequency terms is dependent upon the frequency. So it is generally affect that. So next question here. The speed regulation characteristic of two generators connected in power system are as follows. G1 120 MVA 60 Hz, R1 is equal to 0.05 Hz per unit on machine base. Okay. Yes, sir. And G2 is 100 MVA 60 Hz, R2 is equal to 0.08 Hz per megawatt. These two generators are connected in parallel. The equivalent speed regulation of these two generators on 120 MVA base is, we have to find out. So basically we have to use the per system based approach, per unit system based approach. So the first R1, this is the machine base. So G1 will consider as a machine base. So its R1 value will remain same, which is 0.05 Hertz per unit megawatt. And R2 is 0.05 divided by 120 Hertz per megawatt. It's come out to be 0.004166 Hertz per megawatt. Okay, so R2 value will be, it is just a second, we have to use this one 120. Okay, just a second, okay, yes, this is R1. So R1 on the 120 MVA base, it is, then R2, what's the value of R2? It is 0.00. There is some confusion there. Yes, it is that okay, R1 is on 120, so R1 will remain same. Okay, this value has to be changed. This is R2 and its value is on the base 100, so its value will get changed. 0.008 divided by 120. So its value will come out to be how much? 0.008 divided by 120. Just a second. 0.000066 Hertz per megawatt. Okay, so the equivalent R, as they are enacting in parallel, so it will be 1 upon R1 plus 1 upon R2 minus 1. So if we solve it for that, so 1
divided by R1 plus 1 divided by 0.000066. So 1 divided by and its value come out to be 151.515 and 1 divided by, just a second, let me get it for you, plus 20. Then we calculate the inverse of this. It is 20 plus inverse. So equivalent art. Equivalent R is equal to 0.000659 hertz per unit megawatt. So this is the final answer of this question. Okay. Now moving on towards another question. Consider a two area system connected with a lossless line. Actually I have, okay, okay, we have solved this question here. Actually the data is R1 is equal to 0.03 per unit. We initially solve it. We have to calculate another thing here, which I will just write it for you. And the base V is 100. Okay, in the previous question, like with this much. This question here, this is the same question, but at that, in that question we calculated the per unit deviation, sorry, frequency value. But here what we have to find, we have to find the, in this question, steady state power flow. And same, the nominal frequency is 50 hertz. Okay, so the solution here is, so basically in that question what we calculate the frequency deviation. Okay, now we have to calculate the steady state tie line power. So here del P mechanic is equal to minus del F by R1. Okay, so here what is del F? Just a second. Okay, what we calculated the del F in previously, we use that value and we calculate the value here. In per unit value, what we calculate 0.000952. Okay, so same value we will use because we will calculate first in the per unit. 0.00952 divided by R1 0.03. Okay. Now, moving on towards the this value, it come out to be, let me calculate it first. 9152 divided by 0.03. It come out to be 0.03051 per unit. Okay. And at the steady state, del P max 1 is equal to del P max minus del tie line of 1 to minus del PL1 is equal to d1 del F. This is the equation we already solved by using the transfer functions in previous lecture. Therefore, del P tie, which is 1 2, is equal to del Mac 1 minus del PL1 minus d1 del F. Okay. So what is del MP1? We just calculated 0.03051 plus PL1. What it is PL1? In the first area there is a decrement of 100 megawatt, 10 actually 10 megawatt. So we just calculated over there, but we calculated this value. We just use it in the, because both questions are in the continuation. Then minus d1.8 into f we already know, which is 0.00095152 del f. So if we solve it, del p tie line 1 2, it's come out to be, let me calculate it first for you, 0.03051 and plus 0.10 comes out to be, the first term comes out to be 0.13051 minus, which is zero point 0.8 into 9152. So it will be plus 0.00073. Actually, this whole process will become minus and it will become plus. So plus 0.131 per unit. This is in the per unit. So we will change it into the value. So we will multiply it by 100. So tie del P tie comes out to be 13.12 megawatt. As we know, the base MVA is 100. So this is the steady state tie line power. Hope you have get to know the concept uh, around this, how we can proceed in any other question. So this is the final answer.
So let me give you one more question. I think this is the second last lecture of this course. After this, only last chapter will be there. So, okay. Question. The Laplace domain representation of ACE for a two-area system is first del F1 is minus del F2, B P tie del F plus B1, let's say this is B1 del F1, C S del F and D R del F S. So we have to get the what is the correct representation. So basically, solution ACE in area, any area, is equal to tie line power deviation, tie line power deviation plus frequency by stem. So here frequency by stem is there, this is there, so B is the correct option. Now in the next question, let me give you. So what is the role of synchronizing coefficient in the tie power line equation? Okay, so first option is determines system inertia, B damping rate, C power transfer to phase angle difference, and D power transfer to voltage magnitude. So synchronizing coefficient क्या होता है? Which is V1 V2 upon X. This is यही तो था synchronize. तो ये क्या करता है? In a tie line power, you should know that it is T del 1 minus del 2. It relates the tie line power to the difference of the equation. So C is the correct option for this question. Okay, so I hope you have understood these things, and I will provide some more questions in this PDF so you can clearly understand. Okay, so another question here. Okay, I will give you one more question. So next question is a system with D is equal to zero point 0.8 per unit and R zero point 0.04 Hertz per unit megawatt experiences a zero point 0.2 per unit load drop. Calculate the steady state frequency rise. Okay, options are Okay, we will directly solve it. The solution is, we know that del F is equal to minus del PL divided by D plus 1 by R. We know what is del PL, which experiences a zero point 0.2 per unit load. So zero point 0.2, it is all in per unit. D is zero point 0.8, R is 1 by 0.004. So zero point 0.2 divided by zero point 0.8 plus 25. It come out to be, it's comes out, let me check it first for you. 0.2 divided by 25.8. Just a second. Okay, yes. So it will, if we multiply by 50, its value comes out to be 0.387. We can say that zero point 0.4 hertz. So okay, we multiply it by 50 because we have to calculate the steady state. This will give the change, otherwise it will give the, if you multiply it by 50, it will give the steady state frequency change. So how much values comes out to be zero point 0.4. So due to this, there will be a change in frequency of zero point 0.4. Okay, so with this, I end today's session. Okay, I have solved various type of questions in this. Okay, because the concept I have already told you about basically. So uh, there will, I will give you more I will supply various questions in this PDF, so you are with answers, and you can go through this those questions also. If you want to ask any question regarding that, we can come and join in the next session. Okay, next week, which will be, I think, the last session of our lecture. Okay, if you have any question, you can ask. Otherwise, feel free to leave. Thank you for joining.